Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 10, Projective Transformations of Two-Dimensional Forms. Section 102, Problems of the Third and Fourth Degrees. The problem of constructing the points of intersection of two conics in the same plane is, in general, of the fourth degree, according to the classification of geometric problems described in Section 83. Indeed, if one of the coordinates be eliminated between the equations of the two conics, the resulting equation is, in general, an irreducible equation of the fourth degree. Footnote: in this section, we have made use of Amadeo Lezioni di Geometria Proiettiva, pages 436-437. Some of the exercises are taken from the same book, pages 448 through 451. Moreover, a little consideration will show that any equation of the fourth degree may be obtained in this way. It results that every problem of the fourth degree in a plane may be reduced to the problem of constructing the common points, or by duality, the common tangents of two conics. Further, the problem of finding the remaining intersections of two conics in a plane, of which one point of intersection is given, is readily seen to be of the third degree in general. And any problem of this degree can be reduced to that of finding the remaining intersections of two conics of which one point of intersection is known. It follows that any problem of the third or fourth degree in a plane may be reduced to that of finding the common elements of two conics in the plane. Footnote: moreover, we have seen, page 289, footnote, that any problem of the fourth degree may be reduced to one of the third degree, followed by two of the second degree. A problem of the fourth or third degree cannot therefore be solved by the methods sufficient for the solution of problems of the first and second degree, straight edge and compass. In the case of problems of the second degree, we have seen that any such problem could be solved by linear constructions if the intersections of every line in the plane with a fixed conic in that plane were assumed known. Footnote: with the usual representation of the ordinary real geometry, we should require an instrument to draw conics. Similarly, any problem of the fourth or third degree can be solved by linear and quadratic constructions if the intersections of every conic in the plane with a fixed conic in this plane are assumed known. This follows readily from the fact that any conic in the plane can be transformed by linear constructions into the fixed conic. A problem of the third or fourth degree in a plane will then, in the future, be considered solved if it has been reduced to finding the intersections of two conics, combined with any linear or quadratic constructions. As a typical problem of the third degree, for example, we give the following. To find the double points of a nonperspective collineation in a plane which is determined by four pairs of homologous points. Solution: when four pairs of homologous elements are given, we can construct linearly the point or line homologous with any given point or line in the plane. Let the collineation be represented by pi, and let A be any point of the plane which is not on an invariant line. Let pi of A equal A prime, and pi of A prime equal A double prime. The points A prime, A double prime are then not collinear. The pencil of lines at A is projective with the pencil at A prime, and these two projective pencils generate a conic C squared which passes through all the double points of pi, and which is tangent at A prime to the line A prime, A double prime. Figure 105. The conic C squared is transformed by the collineation pi into a conic C1 squared generated by the projective pencils of lines at A prime and A double prime. C1 squared also passes through A prime and is tangent at this point to the line A prime. The double points of pi are also points of C1 squared. The point A' is not a double point of pi by hypothesis. It is evident, however, that every other point common to the two conics c squared and c1 squared is a double point. If c squared and c1 squared intersect again in three distinct points, L, M, N, the latter form a triangle, and the collineation is of type 1. If c squared and c1 squared intersect in a point N, distinct from A', and are tangent to each other at a third point, L equal M, the collineation has MN for double points, and the line MN and the common tangent at M for double lines, figure 106, it is then of type 2. If finally the two conics have contact of the second order at a point L equal M equal N, distinct from A', the collineation has the single double line which is tangent to the conics at this point, and is of type 3, figure 107. Exercises 1. Give a discussion of the problem above without making, at the outset, the hypothesis that the collineation is nonperspective. 2. Construct the double pairs of a correlation in the plane, which is not a polarity. 3. Given two polarities in a plane, construct their common pole and polar pairs. 4. On a line tangent to a conic at a point A is given an involution iota, and from any pair of conjugates P of iota are drawn the second tangents P to the conic, their points of contact being Q respectively. Show that the locus of the point P is a line L passing through the conjugate A' of A in the involution iota, and that the line Q passes through the pole of L with respect to the conic. 5. Construct the conic which is tangent at 2 points to a given conic and which passes through 3 given points. Dualize. 6. The lines joining pairs of homologous points of a noninvolutoric projectivity on a conic A squared are tangent to a second conic B squared, which is tangent to A squared at 2 points, or which hyperosculates A2. 7. A pencil of conics of type 2 is determined by 3 points A, B, C, and a line C through C. What is the locus of the points of contact of the conics of the pencil with the tangents drawn from a given point P of C? 8. Construct the conics which pass through a given point P and which are tangent at 2 points to each of the 2 given conics. 9. If f equals 0, g equals 0, h equals 0 are the equations of 3 conics in a plane not belonging to the same pencil, the system of conics given by the equation lambda f plus mu g plus nu h equals 0, lambda, mu, nu being variable parameters, is called a bundle of conics. Through every point of the plane passes a pencil of conics belonging to this bundle. Through any 2 distinct points passing, in general, one and only one conic of the bundle. If the conics f, g, h have a point in common, this point is common to all the conics of the bundle. Give a non-algebraic definition of a bundle of conics. 10. The set of all conics in a plane passing through the vertices of a triangle form a bundle. If the equations of the sides of the triangle are L equals 0, M equals 0, N equals 0, show that the bundle may be represented by the equation lambda Mn plus mu Nl plus nu Lm equals 0. What are the degenerate conics of this bundle? Footnote: in connection with this and the 2 following exercises, chiefly Castelnuovo, Lezioni di Geometria Analitica e Proiettiva, Volume 1, page 395. 11. The set of all conics in a plane which have a given triangle as a self-polar triangle forms a bundle. If the equations of the sides of this triangle are L equals 0, M equals 0, N equals 0, show that the bundle may be represented by the equation lambda L squared plus mu M squared plus nu N squared equals 0. What are the degenerate conics of this bundle? 12. The conics of the bundle described in exercise 11, which pass through a general point P of the plane, pass through the other three vertices of the quadrangle, of which one vertex is P, and of which the given triangle is the diagonal triangle. What happens when P is on a side of the given triangle? Dualize. 13. The reflections, whose centers and axes are the vertices and opposite sides of a triangle, form a commutative group. Any point of the plane not on a side of the triangle is transformed by the operations of this group into the other three vertices of a complete quadrangle, of which the given triangle is the diagonal triangle. If this triangle is taken as the reference triangle, what are the equations of the transformation? What conics are transformed into themselves by the group, and how is it associated with the quadrangle-quadrilateral configuration? 14. The necessary and sufficient condition that two reflections be commutative is that the center of each shall be on the axis of the other. 15. The invariant figure of a collineation may be regarded as composed of two lineal elements, the five types corresponding to the various special relations between the two lineal elements. 16. A correlation which transforms a lineal element AA into a lineal element BB and also transforms BB into AA is a polarity. 17. How many collineations and correlations are in the group generated by the reflections, whose centers and axes are the vertices and opposite sides of a triangle, and a polarity with regard to which the triangle is self-polar?
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.